Motivation behind Bcrypt. Technology changes fast. Increasing the speed and power of computers can benefit both the engineers trying to build software systems and the attackers trying to exploit them. Some cryptographic software is not designed to scale with computer power. As explained earlier, the safety of the password depends on how fast the selected cryptographic hashing function can calculate the password hash. A fast function would execute faster when running a much more powerful hardware. To mitigate this attack vector, we would create a cryptographic hash function that can be tuned to run slower and newly available hardware. That is, the function scales with computer power. This is particularly important since through this attack vector, people tend to keep the length of the passwords constant. Hence, in the design of a cryptographic solution for this problem, we must account for rapidly evolving hardware and constant password length. This attack vector was well understood by cryptographers in the 90s, and an algorithm by the name of Bcrypt that met these design specifications was presented in 1999 as useness. Let's learn how Bcrypt allows us to create a strong password storage systems. So, what is Bcrypt? Bcrypt was designed by Neil Provost and David Messiers based on the Blowfish cipher. The B stands for the Blowfish and Crypt for the name of the hashing function used by the Unix password system. Crypt is a great example of failure to adapt to technology changes. According to Usenet in 1976, Crypt could hash fewer than 4 passwords per second. Since attackers need to find the pre-image of a hash in order to invert it, this made the Unix team feel very comfortable about the strength of Crypt. However, 20 years later, a fast computer with optimized software and hardware was capable of hashing 200,000 passwords per second using that function. Inherently, an attacker could then carry out a complete dictionary attack with extreme efficiency. Thus, cryptography that was exponentially more difficult to break as hardware became faster was required in order to hinder the speed benefits that attackers could get from that hardware. The Blowfish cipher is a fast block cipher except when changing keys. The parameters that establish the functional output of a cryptographic algorithm. Each new key requires the pre-processing equivalent to encrypting about 4 kilobytes of text, which is considered very slow compared to other block ciphers. This slow key changing is beneficial to password hashing methods such as Bcrypt, since the extra computational demand helps protect against dictionary and brute force attacks by slowing down the attack. As shown in the Blowfish in practice, so you can have the link of this article, you can read it. Bcrypt is able to mitigate those kinds of attacks by combining the expensive key setup phase of Blowfish with a variable number of iterations to increase the workload and duration of hash calculations. The largest benefit of Bcrypt is that over time, the iteration count can be increased to make it slower, allowing Bcrypt to scale with computing power. We can diminish any benefits attackers may get from faster hardware by increasing the number of iterations to make Bcrypt slower. Bcrypt was designed for password hashing, hence it is a slow algorithm. This is good for password hashing as it reduces the number of passwords per second an attacker could hash when crafting a dictionary attack. Another benefit of Bcrypt is that it requires a solve by default. Let's take a deeper look at how this hashing function works. Bcrypt forces you to follow security best practices as it requires a salt as part of the hashing process. Hashing combined with salts protects you against rainbow table attacks. Are password salts part of your security strategy? So, how does Bcrypt work? Provost and Messiers, the designers of Bcrypt, used the expensive key setup phase of the Blowfish cipher to develop a new key setup algorithm for a Blowfish named X-Blowfish, which stands for Expensive Key Schedule Blowfish. What's key setup? According to Ian Hassen, a software engineer at NVIDIA, most ciphers consist of a key setup phase and an operation phase. During the key setup, the internal state is initialized. During operation, input, cipher text, and plain text is encrypted or decrypted. Key setup only needs to be conducted once for each key that is used. Bcrypt runs in two phases. Phase 1, a function called xblowfish setup is set up using the desired cost, the salt, and the password to initialize the state of xblowfish. Then Bcrypt spends a lot of time running an expensive key schedule, which consists of performing a key derivation where we derive a set of subkeys from a primary key. Here the password is used as the primary key. In case that the user selected a bad or short password, we stretch the password slash key into a longer password slash key. The aforementioned practice is also known as key stretching. What we are going through in this first phase is to promote key strengthening to slow down calculations, in which in turn also slow down attackers. Phase 2. The magic value is the 192-bit value. Orphean Beholder is cried out. This value is encrypted 64 times using xblowfish in ECB mode. With the state from the previous phase, the output of this phase is the cost and the 128-bit salt value concatenated with the result of the encryption loop. And here we have this picture. So in this image we can see the Bcrypt that is taking the cost, the salt, and the PWD. We have the state, we have the xblowfish setup that it takes the cost, the salt, the key. We have the ctext, the Orphean Beholder is cried out. Repeat 64. We have the ctext that is encrypt ECB. It takes a state in ctext and returns concatenate, passing the cost, the salt, and the ctext. The resulting hash is prefixed with $2A $, comma, $2Y $, or the $2B $. The prefixes are added to indicate usage of Bcrypt and its version. The result of Bcrypt achieves core properties of a secure password function as defined by its designers. It is pre-image resistant. The salt space is large enough to mitigate pre-computation attacks such as rainbow tables. It has an adaptable cost. The designers of Bcrypt believe that the function will hold its strength and value for many years. Its mathematical design gives assurance to cryptographers about its resilience to attacks. Regarding adaptable cost, we could say that Bcrypt is an adaptive hash function, as we are able to increase the number of iterations performed by the function based on a passkey factor, the cost. This adaptability is what allows us to compensate for increasing computer power, but it comes with an opportunity cost, speed or security.